Reality isn't fixed. It's co-written by the questions we ask and the measurements we make. The quantum deception pulls back the curtain on how perception can fool us at the smallest scales, and why that awareness matters to every moment of your life. You'll see why particles defy everyday logic, how observation changes outcomes, and what that implies for trusting the world around you. This isn't just mind-bending physics. It's a practical lens on how your brain builds reality and how science tests those limits. If you've ever wondered whether what you see is real, you're about to get a clear, captivating tour through the strange dance between perception and quantum truth. Perception and reality, the quantum question. In quantum experiments, particles display both wave-like and particle-like behaviors, and the mode of observation often dictates which picture you see. Interference patterns arise when a system goes unmeasured, and detection choices collapse those patterns into discrete impacts. In the classic double-slit setup, selecting to measure the path collapses the wave-like spread and erases interference. That flip between possibilities and outcomes feels counterintuitive. This dynamic hints that perception and measurement are braided into what we name reality. The line between observer, instrument, and object becomes fuzzy in the smallest scales. A system can inhabit a superposition, a blend of possibilities, until a measurement yields one definite result. The moment of measurement is not just discovering a state. It seems to create a state in the sense that the prior ambiguity vanishes when information is recorded. Decoherence helps explain how interactions with the environment rapidly suppress quantum interference, letting classical properties emerge without requiring a lone consciousness to notice. Yet observation in physics means any interaction that records information, not merely a human gaze. The discussion then branches into competing stories about what exists independently of how we investigate it. Bell-type experiments show correlations that challenge explanations based solely on local hidden properties, nudging the debate toward more holistic or non-local pictures. Delayed choice and quantum eraser variance push this further, suggesting that choices made after particles are in the apparatus can influence recorded outcomes. The pattern is stubborn. What we can measure changes what seems real, at least in the quantum domain, and our intuitions about separation between subject and object strain under pressure. The landscape of interpretations offers distinct narratives about the same data. The Copenhagen view tends to keep a dividing line between quantum and classical worlds, treating measurement as the bridge to definite results. Many worlds rejects collapse, proposing that all possible outcomes occur in branching universes, so reality multiplies rather than changes form at the moment of measurement. Cubism foregrounds the observer's personal expectations, treating probabilities as an agent's degrees of belief about future experiences rather than intrinsic properties of systems. Relational quantum mechanics adds that properties depend on the interaction history between observer and system. Each approach preserves the predictive power of quantum theory while offering a different sense of what is real when no one is looking. The lack of a single, universally agreed-upon answer leaves room for practical work and philosophical reflection alike. In practice, quantum effects are harnessed by delicate control that preserves coherence long enough to perform tasks, from computation to precise sensing. Every measurement introduces disturbance, which means engineers must balance information gain against state fidelity. Understanding how perception and reality interplay helps design devices that extract meaningful information without destroying the quantum state more than necessary. Decoherence explains why the world we experience appears classical even though its fundamentals obey quantum rules. The ongoing tension between what we can observe and what might lie beyond observation invites humility and active exploration. The quantum question remains vibrant in theory and in the lab, shaping how we interpret outcomes and build technologies that rely on the strange texture of reality. Superposition, possibilities before observation. Superposition is the principle that quantum systems can exist in multiple states at once until measured. A single electron spin can be described as a blend of up and down, and a photon can inhabit a superposition of polarization states. The mathematical description is a wave function whose complex amplitudes encode the likelihood of each outcome. The square of these amplitudes, via the Born rule, yields the probabilities we actually observe. Until measurement, these possibilities are part of a well-defined quantum state, not just a guessing game. The double-slit experiment illustrates how superposition manifests as interference. When both paths are accessible, the amplitudes combine, producing bright and dark fringes. If which path information is obtained, the interference dies away and the pattern becomes a smear of particle-like hits. That change shows how observation and information extraction affect the system, not merely our knowledge. The same principle helps explain why electrons can contribute to outcomes that seem impossible if they were limited to a single route. In quantum computing, a qubit can hold a mix of 0 and 1, enabling parallel evaluation of many possibilities. A superposed state is not a rumor of what will happen. It's the actual probability structure that governs the future. When you measure the qubit, you get one definite result with a probability dictated by its amplitudes. Algorithms use interference to amplify correct outcomes while reducing others. Real devices must be kept isolated long enough to maintain coherence. Otherwise, the superposition fades into classical randomness. Decoherence arises from tiny interactions with the environment that scramble relative phases between states. The practical upshot is that superpositions are fragile in the real world, but careful engineering can extend coherence. Sensors, imaging systems, and communication protocols rely on maintaining coherence long enough to extract useful information. This fragility also feeds the philosophical angle. What we perceive as a definite outcome is the result of many potential futures narrowing to one through observation. The quantum deception, if it is one, is a reminder that observation participates in shaping the seen world. Measurement, the act that defines outcomes. Measurement in quantum physics isn't simply reading a value. It actively chooses one outcome from a spectrum of possibilities. The interaction with a measuring device entangles the system with the apparatus, so the state after measurement appears as a definite result. A spin 1/2 prepared in a superposition can yield a definite up or down when a detector is aligned to a particular axis, and the probability of each outcome follows the Born rule. Before the act, the world exists as possibilities. After, perception anchors one of them. This is the core of the deception. Outcomes feel real and unique, yet they emerge from a web of probabilities and interactions. Some call this tension the quantum deception, a name that hints at how perception shapes reality. The choice of measurement basis does not just reveal a pre-existing value. It helps define what value can be observed. Measure along the z-axis, and you observe up or down. Two observables that do not commute cannot be assigned simultaneous definite values. So reality appears to rearrange itself when you switch axes. Context matters. The experimental setup, the timing, and even the way the results are read out all shape what is observed. In practice, the system never stands alone. The measuring device becomes a larger quantum system that shares correlations with its environment. Through decoherence, the myriad possible states become effectively invisible, leaving a single outcome that seems real to us. That appearance of a definite result is not the system choosing a fact independent of us. It's the interaction with countless degrees of freedom that makes one branch dominant in our experience. The real mystery is that other branches or possibilities persist in the formal description, even as our observation selects one to register. Modern techniques bend around this by using weak measurements, non-projective palms, and carefully designed readouts to extract information with minimal disturbance. In quantum information, measurements are not just verdicts but tools that drive computation and security protocols. Quantum key distribution relies on the statistics of measurement outcomes to detect eavesdropping, while tomography rebuilds an unknown state through many diverse measurements. The measurement story also fuels interpretations that see reality as relational or branching, rather than fixed from the outset. Across labs and devices, the act of measuring remains the practical bridge between the abstract math of a wave function and the everyday sense that something definite has happened. Decoherence, from quantum potentials to classical reality. Decoherence occurs when a quantum system interacts with its surroundings, causing quantum coherence to vanish. The system becomes entangled with many degrees of freedom in the environment, and when we look only at the system, its state is described by a density matrix with suppressed interference terms. Those off-diagonal elements fade away because each possible state becomes correlated with different states of the environment, making superpositions effectively unobservable. What remains is a statistical mixture that captures our practical ignorance rather than a single, coherent superposition. This transformation does not require a physical collapse. It arises from the unitary evolution of the larger system that includes everything around. Consider an electron going through a double-slit apparatus immersed in air. If the air molecules interact with the electron, information about which path the electron took leaks into the environment, and interference fringes fade. The same idea applies to superconducting qubits. Coupling to stray electromagnetic modes erodes the delicate phase relationships that encode quantum information. In each case, the environment acts like a silent observer, recording tiny imprints that, when ignored, leave behind only classical probabilities. The mathematics uses the density matrix and tracing out the environment to reveal a transition from pure quantum states to mixed states, a process that explains why the world appears classical at large scales. This underlying dynamics still obeys quantum laws. Decoherence is not a magic switch, but a consequence of entangling complexity. From this viewpoint, the so-called quantum deception is not about a hidden trick in nature, but about the limits of our access. The brain reconstructs a stable picture by relying on robust, decoherence-resistant states that survive environmental scrutiny. Position, for example, tends to become a preferred basis because it correlates with many environmental degrees of freedom, making it repeatable and predictable. The appearance of a single, definite outcome emerges because multiple potential histories differ in ways too subtle for the environment to preserve as coherent alternatives. While many interpretations tackle what reality is, decoherence explains why we experience a classical world even when the fundamental laws are quantum. Practical implications are evident in quantum technology. Quantum information processing demands strategies to fight decoherence, such as isolating qubits, using error-correcting codes, or employing dynamical decoupling. Researchers also explore decoherence-free subspaces and topological qubits as ways to shelter quantum information from environmental noise. In laboratories, controlled experiments manipulate the environment to either suppress unwanted decoherence or study how it selects a preferred basis and drives the quantum to classical transition. The overall message is that classical reality is not a separate layer placed on top of quantum stuff, but the emergent face of a vast quantum tapestry dyed by interaction with the surroundings. Implications: rethinking truth and experience. In quantum mechanics, particles can behave as waves and as particles depending on how they are observed. The double-slit experiment demonstrates this vividly. Electrons or photons create an interference pattern when not measured which path they take. When a detector is placed to determine the path, the interference disappears and two distinct bands appear. The outcome is not simply a property of the particle itself, but a result of the interaction between the system and the measuring setup. That shifts the idea of reality from a fixed stage to a dependent arrangement. This phenomenon shows that what we call reality cannot be separated from how we study it. Truth shifts from an inherent label to a relational property. Properties of a quantum system do not exist in isolation. They emerge in the context of a measuring arrangement, and different setups can reveal different aspects. Entangled states show correlations that cannot be explained by local properties alone. The information we obtain is bound to the act of observation and the equipment used. This suggests a more nuanced view where reality is partly constructed in the moment of measurement. Decoherence helps explain why we see stable objects in a world governed by fragile quantum states. Interactions with the environment rapidly suppress quantum coherence, making classic outcomes appear definite. Delayed choice and quantum eraser experiments illustrate that what we choose to measure can influence how a system behaves, even when a decision seems to be made after the fact. In industry, this translates to precise control for quantum sensors, error-corrected qubits, and secure communication. These ideas ripple into data interpretation and everyday cognition. In data science and AI, context matters. A model's outputs depend on how data is framed, what features are chosen, and what problem is defined. In medicine, quantum-informed sensors improve imaging and timing, but clinicians still interpret signals through theory and prior knowledge. In daily life, this means trust is earned by understanding the context behind a claim and recognizing that perception shapes memory. The quantum deception invites humility, curiosity, and a shift toward pragmatic, experiment-driven thinking about truth and experience. That's the quantum deception, and here's the bottom line. Reality isn't a fixed snapshot, but something that emerges from the dance between quantum possibilities and how we observe them. The key ideas we explored: superposition, entanglement, the role of measurement, the limits set by uncertainty, and the way decoherence turns possibilities into a single experienced outcome, show that perception plays a powerful role in what we call real. Our brains stitch a stable world from noisy signals, yet those signals are embedded in the strange physics of the quantum realm. If you felt that familiar tug, that two people can witness the same moment and still walk away with different truths, you've met the theme in action. If this sparked new questions, drop them in the comments. If you enjoyed the ride, like and subscribe, and hit the bell so you don't miss our next foray into reality testing. We'll keep pushing at the edges of what feels solid to reveal what might lie beneath. In the next videos, we'll dive into quantum randomness in real-world technologies, peek behind the curtain of quantum computing, and run simple thought experiments you can try at home to explore how perception and physics shape each other. Until then, stay curious and see you in the next episode.